Welcome to the Sustainable Remediation Forum webinar. My name is Kyle Waldron. I'm a current SURF board member and very happy to introduce today's presentation. First, I'll give you a little introduction. SURF is a nonprofit organization whose mission is dedicated to advancing sustainable remedies and practices through collaboration, education, and innovation. And SURF is made up of a number of people from site owners to regulatory agencies, academia, consultants, specialty vendors, and the public. So for more information on SURF, feel free to visit our website and or reach out to any of our members, including anybody on the current board. I do see we have a lot of members on the call today, so I would like to say if you're interested in serving on the board, there will be a number of positions open for election over the coming months. So we'd love to have you consider serving in one of those roles. And then, again, look to our website for more information, sign up to become a member or renew your membership at the year's end, because we wouldn't be able to do these great things, including these webinars, without all of your support. If you miss any part of the webinar, it will be posted to our SURF YouTube channel after this, so feel free to go check it out or check out any of our past webinars. But today I'm really excited for the presentation that's on combined technologies to address complex chlorinated hydrocarbon sites. We have two great speakers for you. First up will be Betsy Collins, who is our current Vice President of SURF and one of the driving forces really behind these SURF webinars. So she's an environmental engineer at Jacobs. Her expertise includes site assessments, remedy design, remedy implementation, and then of course with an emphasis on sustainability and optimization. Her co-presenter today is Monica Fulkerson, who is a PE and serves as a Senior Technical Consultant and PM for Jacobs. She works with federal and private clients specializing in site management and remediation projects. Her expertise includes implementing a number of innovative technologies, including subgrade biochemical reactors, which if you haven't seen those presentations using solar power, they're pretty impressive. Enhanced bio, Prbs, constructed wetlands, just to name a few. So with that, I'll welcome our speakers and turn the presentation over to you, Betsy.
Kyle, thank you so much for the introduction. We really appreciate it, and we appreciate this platform today. And we're excited to talk to y'all today about the need for technology combinations to achieve remedial action objectives. We're going to focus on these two case studies, two complex chlorinated hydrocarbon sites at a federal facility. And so here's the snapshot of where we're going today. We're going to talk about how we got here as an industry, why we need combined technologies. Then we're going to get into these two case studies. We're going to talk about what makes these sites complex and why they need these technology combinations to achieve their objectives. But we're also going to talk about the exit strategies and the optimization strategies that are in place to move these sites towards closure. So why combine technologies? In the beginning, we had simple sites, and simple sites required simple solutions. So it's kind of where our industry began, and for the most part, we've knocked out these simple sites. And the sites that remain, we have good processes and good procedures in place to knock them out. But what we're left with now are these more complex sites that require a more complex solution. And there's a lot of factors that contribute to the overall complexity of a site. Some of those factors are listed here, maybe extensive contamination, heterogeneous geology, large releases or large source areas, multiple or recalcitrant contaminants. Maybe it's been a long time since the release occurred. Additional factors that can contribute to complexity include restrictions on the physical placement or the operation of remedial technologies, as well as challenging expectations We have challenging expectations from our regulators, from our cleanup goals themselves, and also from our community. And the more of these factors that are in place, the more complex a site becomes and the more complex a solution may need to be. And remedial success at these sites ultimately depends on integrating multiple remediation and risk management approaches along with long-term management. And so perhaps you're thinking to yourself, I joined this call about combining technologies at complex sites because this is a challenge that I'm facing. But what the heck does it have to do with sustainable remediation, and why is SURF even hosting this topic? So here's my argument. A site with substantial technical and non-technical challenges typically has a longer remediation time frame, a higher remediation cost, and a larger environmental footprint, particularly if these site challenges are not being adequately understood and addressed early on. But if instead we look at these sites with a sustainability lens, what we see is that these complex sites really have a greater potential for cost savings, a greater potential for environmental footprint reductions, a greater potential for beneficial land reuse and other societal benefits. And what we're really talking about is adaptive site management. And this term, if you're not familiar with it, it's referring to a comprehensive, flexible, and iterative process that's used to manage our remediation sites and manage our remediation process. And adaptive site management can be used to make decisions in response to remedy performance, and is taking into consideration change, because our sites are never static. They're constantly changing. We see changes in site conditions, changes in the conceptual site model, in our technology's performance, and in technological advances over time. In 2017, the ITRC released their guidance, Remediation Management of Complex Sites. In this guidance, it outlines a process which is shown in the flowchart on the right, and that process includes setting short-term interim objectives along with long-term site objectives that are reflective of both technical and non-technical challenges. And the remedial approach, it may involve multiple technologies like we'll discuss today, or it might include changes in technologies over time. Comprehensive planning and scheduled evaluations of remedy performance help decision makers track progress and adjust the remedy if needed, so that we're able to stay on track to achieving our short-term interim objectives. Long-term planning, it also improves the timeliness of our optimization, our reevaluations, and our transitions to other technologies or to other contingency actions. For both of the case studies today, we're going to discuss the following. First, the remedy components. How was the site split up and why each of these remedies was chosen for each area? But we're also going to talk about the exit strategy, those interim objectives for each remedy. But before we even get into the case studies, I want to lay it out really clearly. What was the benefit of applying combined technologies and other adaptive site management techniques? We've been able to achieve distinct remedial objectives in different parts of our target treatment areas. We're able to account for varying site characteristics. It provides us flexibility with operations and maintenance. We have a clear transition to monitored natural attenuation. And all of these in combination ultimately reduce the cost, the time to clean up, and our environmental footprint. And as we walk through these two case studies, we are going to go out of our way to point out instances where our strategies had sustainability benefits. And so with that, I'll turn it over to Monica to start talking about our facility background and our first case study.
Thanks, Betsy. The area of focus for our presentation is a large federal facility in eastern North Carolina The facility was commissioned in the early 1940s and remains active today. CERCLA investigations and remediations have been underway since the mid-1990s, and currently we have about 50 active environmental sites across the nearly 240 square mile facility. These include chlorinated solvent sites, sites with munitions and unexploded ordnance, and sites with emerging contaminants. Here's a quick side-by-side of the key characteristics of each of the sites that we're going to discuss. The first is a former dry cleaning facility, naturally with PCE and its daughter products as the contaminants of concern. At this site, product was released from the facility directly into the subsurface and over time sank to a depth of 180 feet. The dissolved plume extends across approximately 51 acres, and the receptors are nearby residents, industrial users, as well as a downgradient creek. Site number 1 is located within a heavily congested area with lots of buildings, utilities, traffic, including the facility's headquarters and police department, so perception is important. The second site is the former motor pool and Defense Reutilization and Marketing Office, or waste disposal area. At this site, product was released to the ground surface from various historical waste management activities and migrated to a depth of 60 feet below ground surface. COCs, including 1122 tetrachloroethene, TCE, and their daughter products are detected in groundwater across approximately 50 acres, and the receptors include industrial users and a different downgradient creek. Site number 1's challenges are primarily above ground, while the complicating features at site number 2 are below ground as a result of a discontinuous confining unit influencing the fate and transport of the COCs. So let's begin with site number 1. As I mentioned, the site's a former dry cleaning facility which used above and underground storage tanks to hold PCE for dry cleaning operations. It's believed that PCE was released from the storage tanks directly or via discharge to an underground sewer line. Investigations started at the site in 1996, which identified PCE and its daughter products in soil and groundwater. For the purposes of better understanding and remediating the site, 3 treatment zones have been established. We have the source area, which consists of impacts at depths of 5 to 40 feet, where PCE appears to have migrated vertically from the former dry cleaning building to an underlying clay unit approximately 20 feet below surface. Some of the dissolved phase COCs have passed through that clay, but most mass is observed to migrate horizontally on top of the clay to the west by groundwater flow. The next zone is the deep dissolved plume. This consists of impacted groundwater down gradient from the source area, which extends deeper and with higher dissolved phase concentrations of COCs at depths ranging from 40 feet all the way to 180 feet. The third zone is down gradient with lower concentrations of COCs in groundwater with impacts limited to 40 to 60 feet below ground surface. The former dry cleaning facility was demolished and a non-time critical removal action was conducted in 2005-2006 to treat the source area. Soil mixing was conducted using large diameter augers to blend in a slurry made of 0 valent iron and bentonite to the top of that confining unit. The ZVI stimulated abiotic reductive processes, while the bentonite acts to reduce the conductivity of the treatment area, increasing the hydraulic retention time for the treatment of impacted groundwater and reducing the inflow of clean water from upgradient. We've been monitoring this site for more than a decade, and we see indications of continued treatment. And you can see here on this plot that we've had a dramatic reduction of PCE with 99.9% reduction in soil, and between 91 and 100% reduction in groundwater. While the soil containing NAPL in the source area was successfully treated and bound, the dissolved plume is still expansive. Conditions above and below ground in each portion of the site were different, so multiple groundwater treatment technologies were selected in the record of decision. For source area groundwater surrounding the soil mixing zone, enhanced reductive dechlorination via vertical injection wells was selected to treat high COC concentrations at shallow depths. ERD was selected to take advantage of the halo of reducing conditions resulting from the ZVI soil mixing treatment. A total of 120 injection wells were utilized for distribution of emulsified vegetable oil in this area. As groundwater flows to the west, the confining unit pinches out, and we see the COCs waterfall over the end of that clay unit and dive to 180 feet at elevated concentrations. To treat this area, in situ chemical oxidation was the selected remedy. Permanganate will be injected via 10 horizontal injection wells stacked in 3 columns perpendicular to groundwater flow and complemented by a recirculation system consisting of 8 downgradient extraction wells to pull groundwater for reinjection into those horizontal wells in a closed loop. ISCO was identified as the preferred technology because conditions in this portion of the plume were naturally oxidizing and because of permanganate's ability to quickly reduce COCs in groundwater. Horizontal wells were selected to more efficiently deliver the permanganate across the large volume that required treatment at depths ranging from 40 to 180 feet, while minimally disrupting the building occupants in the area. Recirculation will be used to enhance the permanganate distribution, thereby optimizing the number of horizontal wells required to make contact across the full treatment area. This recirculation component allowed us to reduce the number of injection wells from 17 to 10, representing a savings of approximately 1.75 million in drilling costs. And it also reduces the time for us to achieve contact with the full treatment volume from 3 years to 1 year. In addition to those metrics, the recirculation approach yields tangential savings in materials, waste, personnel travel, and so forth. Then, as impacted groundwater continues to move down gradient, COC concentrations are detected at lower concentrations at intermediate depths. The dissolved plume continues to migrate towards the site boundary and a nearby water body. Here, a biobarrier was the selected remedy, and it's established by the injection of emulsified vegetable oil through a wall of vertical injection wells. The biobarrier is intended to polish the groundwater before it leaves the site. So I'm going to pause for just a moment and talk a little bit about exit strategies and sustainability in general. While it seems obvious, exit strategy is important from a sustainability perspective. When we look at the rods, the early rods from the 90s, exit strategies are sometimes missing. And in some cases, we are operating well beyond their practical effectiveness simply because the rod didn't include an exit strategy, and administratively, we can't find our way out of continued operation, consequently expending resources without a significant return on our investment. The act of remediation itself leaves an environmental footprint, so clearly, defining the limits of each technology allows us to put some boundaries on this. Okay, so back to my site. Because of the objectives for each remedy, because the objectives are different, so are the milestones to transition from active treatment to monitored natural attenuation. It's in the stakeholders' best interest to get to this point as quickly as possible. So it was important to put thoughtful milestones in place and gain team endorsement early on. For the source area and deep dissolved plume, the first two zones, the reduction of high COC concentrations is the primary objective. But the challenging question was, how much do we have to reduce the concentrations to protect the downgradient receptors? We used predictive modeling to determine the concentration at which the COCs would attenuate to acceptable concentrations before migrating off-site, and we're calling those our active remediation goals. But we know that models aren't a precise tool, so we've built some flexibility into the decision logic for switching from active treatment to M&A based on multiple lines of evidence. This includes the mass reduction component, but also considers plume stability and sustained favorable geochemical conditions. Downgradient, our objective is different. The intention is to help mitigate downgradient migration of COCs not treated by source area or deep dissolved plume remedies. So for this one, active treatment can be discontinued when the influent COC concentrations are protective of the downgradient receptors, or aquifer conditions suggest that biodegradation can be maintained naturally. And at that point, M&A can take over until the COCs are reduced to levels suitable for unrestricted use. So where are we today with this site? The ROD was signed in 2019 and the remedial design was completed earlier in 2020. Implementation is ongoing and is expected to be completed by the end of next quarter. Then the site will be evaluated every 5 years to determine if the remedy remains protective. The 5-year review will also serve as an opportunity to review our long-term monitoring data. If the data indicate that natural attenuation will require unreasonable timeframes for active treatment after active treatment is complete, optimization of the remedy may be required to increase the degradation rate of the remaining contamination. So now I'll turn it back over to Betsy to talk about site number 2.
Thanks, Monica. We'll see if I can click all the right buttons to get it back. And here we are. Case study number 2. As Monica previously mentioned, this site is the former motor pool and a waste storage area. The site operated as the motor pool until 1988. And during this time, records indicate that they were using various solvents, including TCE, to clean parts and clean equipment. After that, the site operated as the Defense Reutilization and Marketing Office, or DRMO, from 1988 until 2000. And if you aren't familiar with the DRMO, it's basically a well-organized junkyard. They're responsible for taking equipment a unit can't use anymore and either reassigning it to other units or selling it or scrapping it. And during this time, records indicate they were storing scrap and surplus metals, electronic equipment, vehicles, rubber tires, fuel bladders. Investigations here started in 1996, and as Monica mentioned, it identified 1122 PCA, TCE, and their daughter products in soil and groundwater. And they were detected at concentrations indicative of NAFL. So as you can see, we're already starting to check off some of these complex site boxes. We're looking at multiple spills of different contaminants. The contamination happened over the course of decades through site use, and that contamination occurred decades ago. The source of contamination here is a little bit less specific, but generally we do see it originating in that storage yard area of the site. The mass migrated vertically to the clay unit, but unlike at the first site, here the clay unit is discontinuous. And so because of that, the distribution of the contamination is less predictable. We've got mass that's sitting on top of the clay, mass that's bound up within the clay. There's mass that's migrated vertically into the deeper aquifers at the site, and we've also seen mass transported laterally via groundwater flow away from the site and towards this downgradient surface water body. Overall, we're looking at a 50-acre plume with contamination up to 60 feet in depth. So once again, we're taking off these complex site boxes. We're looking at a really large area, heterogeneous geology, and sensitive downgradient receptors. Like the first site, the source area here was addressed first, and it was addressed through non-time critical removal actions. In 2003, while investigations at the site were still ongoing, electrical resistance heating was implemented to target widespread impacts to the first several feet of soil across the storage yard. We estimated that in total, about 48,000 pounds of contaminant mass was removed during this non-time critical action. But these ongoing site investigations revealed that we still had elevated COC concentrations all the way down to the top of that clay unit. And so a second non-time critical removal action was conducted. And again, we conducted soil mixing using large diameter augers to blend in the zero valent iron and the bentonite. And again, this technology proved to be really successful. We saw up to a 99.7% reduction in total COCs in soil and a 92.3% reduction in groundwater. During the soil mixing, we were also able to implement a sustainable best management practice. By using a byproduct of steel recycling, we minimized our cost and we also maximized the use of recycled materials. So once again, we found ourselves in the position of having treated the NAPL in the source area, but having remain a large dissolved plume. And so because of that, multiple treatment technologies were selected in the ROD to address these contaminants at their different stages of fate and transport. So we started with the source area groundwater. And for this area, the selected remedy was air sparging via 2 horizontal wells to target the elongated portion of the plume, as well as 3 vertical wells to target our isolated, deeper impacts. To address groundwater that had already migrated down gradient from the source area, 2 hanging permeable reactive barriers were constructed perpendicular to groundwater flow using a blend of mulch and gravel. And these are the 2 brown lines shown on the map. The idea in this area was to make the PRB a preferred pathway and create reducing conditions within the wall itself to treat groundwater as it flows through. Now, we already knew at the time of implementation that, of course, some groundwater had migrated beyond where the PRBs were being installed. And so a third component of the remedy was to address the surface water body itself. And so here, we incorporated 6 in-stream aerators to strip the volatile organic compounds from the stream directly. And last, but certainly not least, we had everywhere else. And the areas of the groundwater plume that fell outside of the active treatment zones became part of the monitored natural attenuation program. Again, our active remedies are serving distinct purposes. And so the criteria for shutdown are unique to each one. For the air sparging system, we established at the time of remedy implementation that air sparging would be discontinued when all COCs were reduced below 100 parts per billion within 50 feet of the wells, or when COC reduction demonstrates asymptotic trends. And the second criteria, the asymptotic trends, is really important. It's critical because it provides us that flexibility that Monica was discussing to discontinue the remedy in the event that the air sparge doesn't perform the way that we expect. And I wanted to take a moment to touch on the annual impacts of running this air sparging system. There's this misconception that sustainable remediation means doing nothing, or that it means it's going to take longer to clean up your site, or somehow it means both of those things and is also more expensive. But what we're actually talking about is a balance of the triple bottom line. Active treatment in these higher concentration areas is absolutely worth the cost and worth the environmental footprint because it's reducing our time to site closure and it's cleaning up contamination. But once we've reached the point of diminishing returns, whether that's because concentrations have decreased substantially or because trends have become asymptotic, we need to have that path to turning the system off so that we aren't hit with these large costs or these large environmental footprints. Our maintenance approach and exit strategy for the PRBs is a little bit different. We're monitoring this area semi-annually and looking for changes not only in COC concentration, but also in ORP and in total organic carbon. And the idea behind this is that if the data suggests that the wall is no longer creating reducing conditions, then we can go in and replenish it. And for the PRBs, we'll discontinue that maintenance when the water that's entering the PRBs is reduced to levels that are suitable for unrestricted use. And similar to what Monica said about rods previously, this is different than I've historically seen written in rods. In similar examples, I've seen a rod state that a barrier similar to this would be replenished at a fixed rate, say every 2 years. And these statements give us no room to address the actual site-specific conditions, the conditions that we know are going to change throughout the life cycle of the project. But with this approach, we're able to replenish the PRB as often or as seldom as the actual current site conditions dictate. Similarly, aeration of the surface water is going to continue until the COCs are reduced to levels protective of unrestricted use, and that allows us to maintain that our contamination isn't migrating offsite. The remedy has been in place at this site since 2014. So we've got about 6 years of operation and long-term monitoring data. The map you're seeing up here in the upper right-hand corner is showing TCE prior to remedy implementation next to a couple years post-implementation. The concentrations in this source area, they continue to decline, but the air sparge is still operational. We haven't reached either of our thresholds. We have not reached asymptotic trends, and we also haven't reached the 100 parts per billion within 50 feet of the well. COCs are also effectively being treated by the downgradient PRBs. After 3 years of monitoring, those TOC concentrations did decline and the wall was replenished. And we did that by pushing in PVC screens via DPT, and we fed in emulsified vegetable oil by gravity flow over the course of several months. Courtesy of very slow groundwater movement, COCs do continue to be discharged to the surface water, despite the success of the air sparging and despite the success of the PRBs. But because the aerators are functioning as intended, all COCs are being stripped from the surface water prior to leaving the site. I also wanted to take a moment to point out another sustainable best management practice that we've implemented since the implementation of these remedies. We've transitioned from low flow groundwater monitoring onto collecting our groundwater samples via no purge sampling technology. We're using snap samplers and passive diffusion bags, and that eliminated the generation of hazardous waste, but it's also just reducing our IDW costs and associated footprints. So as we wrap up our 2 case studies, I'm going to turn it over to Monica for our first set of key takeaways on the case studies themselves.
Yeah, key technical takeaways first. These 2 case studies show how one size does not fit all when it comes to remediation strategy or emplacement technology. Successful site management requires an aggressive source treatment combined with multiple remediation technologies to effectively address these expansive dissolved plumes. By splitting the plumes into smaller zones, we were able to optimize based on existing aquifer conditions and by addressing multiple remediation objectives concurrently. A combined technology approach allows for flexibility in transitioning from active remediation to monitored natural attenuation. And all of this comes together to reduce the overall remediation footprint. So Betsy, your final thoughts on tying this back to sustainability?
Yeah, I couldn't help myself. You know, at the end of the day, our complex sites are only becoming more complex. Some of the factors that are adding to this complexity include the impacts of extreme weather events and wildfires. We're thinking about how we can build resiliency into our site management approaches, build resiliency into how and why we combine different technologies. You know, another one of the greatest challenges that's facing our industry is how to effectively and sustainably remediate emerging contaminants, PFAS. We all know these substances are composed of increasingly complex compounds that are degrading in our environment to even more complex and challenging daughter products. And all the while, we also need to be taking into consideration the ethics and the intergenerational equity of our actions, whether the nature or duration of our remedial works is resulting in the transfer of contamination or their migration to future generations. But I do really believe that instead of viewing these complexities as a challenge, the sustainability lens allows us to view these complexities as an opportunity. And I do hope these case studies showed how by combining technologies in combination with other adaptive site management strategies, we can be led to faster and greener and cheaper and overall more sustainable solutions. And so with that, we'd love to take some questions or have a conversation about what y'all are seeing or thinking about in this space. Oh, Chris, I think you are on mute.
Absolutely. Yeah, thank you guys. Yeah, that was a great presentation. Everybody on the presentation here, feel free to submit your questions via the questions window. We have a few to get us going, but we have plenty of time to take as many questions as you guys would like. So I'll start off with the first one here. What were some of the risks considered when selecting the types and sequencing of the remedial actions at each site?
You want to talk about the first site, Monica?
Sure. So at the first site, we talked about how a lot of our challenges were above ground. We had a lot of occupied buildings in the area. There were headquarters and police department and other activities that we didn't want to disrupt through our remedial action. So safety and perception were key considerations. We needed to make sure that the remedy could be executed in a manner that didn't disrupt and while also protecting these nearby workers and residents. So that played into the selection of emulsified vegetable oil and ERD over some of the chemicals involved with an ISCO type application in that particular zone. But also, it's important to mention we've had really tremendous results with air sparging at this facility. But because we're in this occupied area and the VI pathway had been observed to be complete in occupied buildings in this area, we decided to implement a remedy that didn't exacerbate that issue. So I would say the risks that we took into consideration were the above ground components and logistics. Betsy, you want to touch on the other one?
Yeah, we had a lot more flexibility at the second site. You know, Monica touched several times on what was going on above ground at the first site, and we didn't really talk about it with the second site because there's really nothing going on. We've got an empty lot, and even with the dissolved plume, we're looking at empty fields, and so we have a lot more flexibility, and that does speak to why we were able to choose air sparging, because we didn't have to worry about those above ground receptors. And so here we were able to balance the active treatment of our higher concentrations with the passive treatment of lower concentrations. But you know, I'd say one of our biggest concerns was keeping the contamination from migrating off-site, and this remedy allowed us to mitigate that risk.
All right, thank you. Next question, how do you balance the objectives of source mass removal and risk reduction for downgradient receptors versus achieving site closure?
Sorry, say it again.
Okay, how do you balance the objectives of source mass removal and risk reduction for downgradient receptors versus achieving site closure?
I don't know. Do you have any thoughts, Monica?
Always. You know, I think it's probably a site by site issue, because I mean, clearly you can't get to site closure until you take care of your source. You can manage the periphery at your site. You can, but understanding that that's going to be a long-term management situation, and you might be, that might be fine. It might be the type of site where we're happy to commit to an annual cost year over year as opposed to a larger capital cost for source removal. But until that source removal, until that happens, we can't begin to talk about site closure. So the balance is, I think it has to be the restraints of the project, the budget, the stakeholder investment, the motivation is if site closure is the goal, then we're going to hit it with the heavier hammer. But if long-term management is the objective, then we can monitor the periphery.
Yeah, I think that's a really great point. What jumped out at me was the stakeholder engagement from the very beginning, understanding who the stakeholders are and what the expectation is, what is the desired outcome, what's the realistic desired outcome.
Yeah, thanks. That kind of leads into the next one. Did you guys see any hurdles, or were any hurdles encountered when trying to achieve that stakeholder buy-in?
Yeah, this is a special team. This facility has a really effective stakeholder partnering team. It includes the facility and the regulators and the supporting consultants, and because of that, as a team, we've been working towards, you know, these win-win solutions for many years, starting from the very beginning of the process. So when we get to the ROD stage and beyond, we're not really encountering resistance in the strategy, because it really is a teamwork approach.
Okay, yeah. So what was considered prior to deciding to remediate, since that could present a big opportunity for sustainable remediation? I think decisions and what remediation type was used, et cetera.
One thing we had talked about, including in the presentation and decided against, was the use of site-wise during the remedy evaluation process. So a full site-wise assessment was done of all the remedy alternatives, and the way the site was split up, we then had alternatives, of course, for each site. So the source area had 2 or 3 alternatives, and the downgradient area had 2 or 3 alternatives. And you know, I found universally that the site-wise results are not a huge driver in remedy selection, but they are a really great opportunity to identify where our greatest impacts are coming from and be able to reduce the footprints on the back end, implementing sustainable best management practices or other strategies, to like implementing the no purge sampling technology. You know, when we're in a long-term monitoring situation, the sampling itself can really have a large footprint. Any other thoughts, Monica?
The only other thing, you sort of touched on it. I was going to mention that this facility did work through the ASTM greener cleanups self-assessment, and we work through those best management practices. Like Betsy said, you know, these are things that we think about through the course of remediation, but just that this particular facility deliberately went through that exercise to see if we could work in any of those BMPs to not just the remediation approach, but investigation and remediation.
Which is a really great shameless plug for the SURF case studies. On our final wrap-up slide, Kyle will have a link to the SURF case studies, and we did a whole case study on the ASTM standard process going through for this facility.
Another question, how successful have you been in obtaining ROD amendments at sites with fixed approaches or unrealistic goals? And what have been effective strategies for getting that at these sites, if you have?
Oh, Monica, I'm pushing that on you.
At this particular facility, we are working on, we've got one, maybe two operable units that are working through the amendment process. So I mean, again, I think it goes back to engaging the team early on, and everything we're doing with team concurrence and endorsement so that we don't find ourselves down a path and not have everybody on board. We are, so at one site in particular, we've got a pump and treat system that's been operating since the 90s that has been asymptotic for years, and we just can't seem to find our way out of operating this system. We're actually in the middle right now of a rebound monitoring study where we've turned that system off, and we're trying to show, you know, on a temporary basis that look, we're going to turn this system off, and the plume's not going to change that much. It's not a hydraulic containment type situation. It's a mass removal remedy. So, you know, we're kind of going baby steps and trying to take advantage. It ties back to adaptive site management and recognizing that the sites aren't today what they were in the 90s when these rods were written, and just trying to work with the technologies that we have available now and what we know about source removal and long-term management of sites to try and move these forward. So as far as how effective we've been yet, to be determined, but optimistic that we're going to be able to move forward and do the right thing at these sites.
How much public input was there at these facilities?
You want to do that one, Monica, or you want me to?
Oh, they've heard from me. You go ahead.
Okay, well, you can jump in if I forget anything. So we do have a community group that meets annually, and it's a dedicated group. Many of them have been involved for many years. But you know, the nature of a facility like this is that a lot of the community comes and goes. They don't always stay for a long time. They're not always around to see the full evolution of the process. So while the community, I think, is very well informed, there's a robust community involvement plan and a robust community group. I think it maybe is a little bit more, they're informed, but they are not drivers.
Yeah, we keep getting them, so I'll keep asking them here.
Amazing, I love it.
Yeah. Do you believe that the remediation materially reduced the risk and improve the risk profile presented by the site?
One more time.
Yeah, I just sent it to you guys too through the chat here, so.
We'll see if we can even find it on our That was crazy
Yeah,
good.
yep. Do you believe that the remediation materially reduced the risk and improved the risk profile presented by the site?
I do. So I do believe that we're making major improvements. I mean, when we're talking about removing tens of thousands of pounds of product, I think that is it's really critical. But I also think that all the pieces of the remediation are really critical. That's what I think is important. You know, we've got a system removing mass, which is great. But equally important, we've got systems in place. You know, I'm thinking about the second site where we're making sure that contamination doesn't then migrate off site, which is having, you know, maybe untold non-impact on downgradient receptors of all kinds.
I'll go ahead and add to that. I think the flip side is the last risk that is going to remain at these sites are potable water use risks. And those are going to be our most stringent, you know, just before we get to a place of unrestricted use. So in that sense, we do have a ways to go before we're ready to walk away from these sites, but we're doing this in concert with land use controls. So as you know, immediately when the remedy was implemented, these waters are not being used for potable use. So effectively, we've eliminated that pathway. But you know, to the spirit of the question, you know, do acknowledge that it's going to be a little while before we get to a point where we're able to walk away.
All right, yeah, next one. What could be the unique challenges at non-federal sites? You know, what would be the role of stakeholders and especially communities in the decision process? And it does sound like you did have a pretty robust community presence especially for a federal site, but how about, you know, non-federal sites with maybe a little more public interaction?
Yeah, I think it really all comes down to communication, and that can really be a struggle. You know, what people want is their backyards cleaned up right now, and that's just not. I mean, it's almost never an option, and so I think that's what's really difficult is working towards like a mutually agreeable final objective, but in a realistic way. I think that can be particularly difficult when you're dealing with communities that have likely been marginalized and not listened to, and you know, have been living or working or being near contaminated lands.
Okay, yeah, one more here. How are you guys sustainably managing back diffusion of the impacted clay? Is that part of the LTM process or?
Oh, that feels like such a loaded question, Monica.
Right.
Yeah, you
Well,
ready to answer it.
I'll offer up that when the soil mixing action that was taken in both of the source areas for these sites did extend a foot or so in, we did lock into those clay units. So I think we're optimistic that perhaps in that upper crust of the clay, we do have treatment, and we are treating all around those areas, and as it back diffuses, the hope is that the conditions are right in those areas to treat. As far as how to sustainably manage it, perhaps this gets into management of the long-term strategy. Betsy, do you have thoughts on that?
Yeah, I guess, you know, when I think about the second site, that is what I see as the sustainable path forward when the source area when the air sparge has been turned off because the groundwater concentrations have been reduced. If we see back diffusion at levels that is causing downgradient impacts, then we've got things like the Prbs in place, or even the surface water aerators. So hopefully those lower footprint in terms of cost and environmental footprint pieces of the alternatives will remain protective.
Okay, yeah, the next one, this is one of the more involved Q&A sessions I think we've had for these SURF. That's great. Are there any plans for redevelopment of the sites now or after a few years?
For the second site, famous last words, there are currently no plans to redevelop, but this is a large area, and I am sure that the client would like to redevelop it into something more usable.
And the first site.
And the first site's already full of stuff.
Yeah, we can't put any more in there. And I doubt they'll go the other way.
The next one here, we have complex sites, management strategies such as site controls, containment, etc., are often recommended or preferred instead of active remediation. Was this considered for these sites?
Yes. I mean, we do have institutional controls in place and land use controls in place. And I think we've got more and less active treatments. We kind of have the spectrum. What do you think, Monica?
Yeah, I agree. And typically one of our sticking points with our stakeholder team is a reasonable time frame to clean up. And these sites were, the concentrations were so high that we were falling outside of that reasonable time frame window. So we had to do something active to help get us there. But that's part of the approach, is to try and do just the right amount so that we can let these other processes and site controls take the lead for the longer duration.
Yeah.
All right, well, I think that's actually wrapping it up for us. I'm gonna turn it back over to Kyle to give a final outro here, and thank you all for attending.
Yeah, thanks guys. I thought it was a great presentation, fantastic talk, and like I said, it generated a lot of great questions. So feel free to rewatch this webinar and watch any of our past webinars on the SURF YouTube channel. It's easy to find it. Just Google SURF Sustainable Remediation YouTube. It'll pop up. Also, make sure you sign up and look at the SURF emails that come out. There's a lot of great information coming out recently, including a new technical initiative that is looking at evaluating footprint analysis tools. So comparing site-wise CEPA, when you would use them, and then potentially identifying some tricks. And so that initiative is just coming together now, so it'd be great if you want to be involved. Also, new case studies, as Betsy mentioned, have been posted on the website, and we are always in search of new ones. So if you have a great one, feel free to reach out to one of us. AHS West will happen this spring virtually. SURF will host some sessions and hopefully another virtual happy hour as well. So look for information on that in the upcoming months. And finally, there will be a open board call, probably early portion of first quarter. Please feel free to join, find out about all these different happenings and how you can get involved. And so finally, next slide. We'd like to say a big thank you to our sponsors that enable us to keep doing these types of things. A special thank you to TriHydro for hosting this webinar and allowing us to use their platform. And with that, thank you, and we look forward to having you all back for the next presentation. So look for that in upcoming emails. Appreciate it.